Hi everyone, my name is Felix Estevez. Today I'll be talking about vibration damping using ferrofluids. It's going to be a quick introduction into some of the most basic systems leveraging magnetic properties and viscous properties of ferrofluids. So the outline of my presentation. Okay, so I'm going to be talking about ferrofluids, just quick introduction and then brief description of the types of ferrofluid-based vibration dampers, and then I'm going to go more in depth into the basics of ferrofluid dampers, vibration isolators, and vibration absorbers. This gentleman on the right is Stefan Pappel, which is the creator of ferrofluids. So he invented ferrofluids at the beginning of the 1960s when he was at one of the NASA laboratories, kind of studying the motion of fluids in microgravity environments. And he proposed the use of magnetic fields to sort of control the motion because they were worried that the fluid wasn't going to get to the engine. So he he graded and find iron oxide particles and mix it with rocket fuel, and they were able to get the fuel to the engine. Of course, that's not how to do it anymore, but ferrofluids are magnetic materials which have super paramagnetic properties, so the name is kind of misleading. And they are pretty much based on a carrier fluid, which can be water, kerosene, etc. And then they have magnetic particles like iron oxide or magnetite. And these particles have a surfactant, so that's what prevents them from agglomeration, as well as they leverage Brownian motion, which is the random motion of particles inside a fluid. And that's why they're not sticking together. But ferrofluids over the time of invention have been used for a lot of things like systems for cooling, sensors, seals, vibration dampers, which are going to be talking about, and even art. So the spooky image on the top right is actually from an exhibition called Passing of Time here at Wonder Spaces in Austin. So the image at the bottom is pretty much what's going on. And what happens is that when you apply the magnetic field to a ferrofluid, then spatially it can try to find the positions where the total energy in the system is minimized. So that's why you get this pretty cool looking shapes. So unfortunately, I'm not talking about the spooky Halloween magnetics. So how can we use ferrofluids for vibration damping? So when you apply a magnetic field to a ferrofluid, what happens is that you change the apparent viscosity of the fluid, and then you can use this for damping applications by using the shear forces between the fluid and some other wall that contains the fluid. So there are different types of ferrofluid as described by Juan et al. Is the reference here. So there are ferrofluid dampers, which are the most simple and probably the earliest ones. So an image is down the top right. The system was used for RAE type satellites for damping of the payload vibrations. There are also vibration isolators, which are typically submerged in ferrofluids, and vibration absorbers, which leverage the geometry of the container of the ferrofluid. And I'm going to go over these more in detail in a second. There's also another type which I'm not discussing, which is vibration energy harvesters. These are actually pretty cool, so I encourage to look into those, but I'm not going to touch on them because they have slightly different focus. So ferrofluid dampers are the earliest, invented in the 1960s. This is from a patent from a long time ago. So the way that these work is that they use the viscous shear forces when the magnetic field is applied. And then the shear, so what happens is that when you apply that magnetic field that's strong enough, when you magnetize this fluid, you kind of lock it in space, if you will. And then as the walls of the container move to the ferrofluid, then you have these shear forces that are bringing the system back to equilibrium. So this image on the right is a pretty good example. You have this ferrofluid inside the hollow wheel. And then as you use these fixed magnets, then this ferrofluid is sort of locked. And then when you have incoming vibrations, then you have a relative velocity between the fixed magnet and the system containing the ferrofluid. So this is attached. So this is a hollow wheel attached to a shaft that can rotate. And then pretty much as the vibrations go through the system, then you're gonna have damping because of the viscosity of the ferrofluid. As you can see, this is pretty simple. The system should theoretically run indefinitely. which is another one of the advantages of this. We don't have to worry about the coefficient of thermal expansion because you don't need to have the wheel filled with ferrofluid. In fact, you can fill it with another immiscible fluid. But of course, one of the disadvantages is that you can really change the magnetic field being applied, and then that's the reason why this is considered a passive system. Any active system would be anything that requires external energy to have the system working or monitor like sensors, etc. Another type of vibration ferrofluid-based vibration isolator dampen system is vibration isolators. Main principle is that you have a system, a vibration source, and whatever is in between that separates those two is a vibration isolator. So this isolates the system from vibrations. So these kind of resemble a spring mass system because the restoring forces are not only the shear forces, but also the inertia of the system that is in contact with this vibration isolator. And you can see this on the example on the right, where they have a piston that's submerged into a ferrofluid attached to a system mass. And you also have to consider forces like buoyancy and magnetic forces, gravity, etc. But let's not go into that rabbit hole. And then in here, what they do in this model is that they have a spring that also provides the vibrations to the system. And then they're able to control the apparent viscosity by using these coils next to it, and then apply different currents to get different magnetic stations. So this is a simulation-based system, and they got pretty significant damping for vibration for frequencies below the resonance of the natural frequency of the system. But it wasn't the case for higher frequencies because it turned out that modeling the apparent viscosity changes is actually quite difficult. And this kind of brings up the importance of picking good materials for this, because if you can better magnetize the ferrofluid, then you're gonna have better viscosity that you can sort of tune. So this will be considered an active system because you can change what magnetic field is going through the fluid. And then the last one is vibration absorbers. These are actually pretty cool because these also leverage the shape of the container of the ferrofluid itself. So in these ones, the ferrofluid is not stationary like in vibration isolators, and the ferrofluid is not fixed like in ferrofluid dampers. What happens is that as the vibration comes in, you move the ferrofluid around, and as you magnetize it, either with a fixed magnet or an external magnetic source, then these dampen the oncoming vibrations. The most simple example that I saw was this one on the top right, by Bush Du Bois et al. So they have this sort of drop, and they have a fixed magnet levitating inside. And then as you have incoming vibrations, what happens is that the magnet and the ferrofluid move. And then as they go into these shallower, narrower regions, then the magnetic forces work to restore the original shape. And while doing that, they also dampen the vibrations on the system. And they tested this by putting this sort of small system on a cantilever. So on a beam, and then one end was fixed, and then it was placed on the other end. So these are the vibrations without the system, and then these are the vibrations with the system. So we can already see that we have relatively good damping. So this works with the fluid motion again, and then the magnetic forces restore the system back in place. So again, the simplicity of these devices is pretty cool, but you also run into the issues that you can't really control how much you can magnetize these and change the viscosity, the apparent viscosity of these fluids. And with that, I'm going to go into conclusions. So vibration dampers leverage the super pattern magnetic properties of ferrofluid, but there's room for magnetic material engineering, maybe different magnetic particles, maybe different carrier fluids, etc. The changing apparent viscosity by use of magnetic fields governs damping, among other factors. We see shape, buoyancy, etc. And then this can be classified as active or passive. So pretty much an active has external energy into the system. You need some sort of sensors or monitor or a source that has different magnetic fields. And these systems are really reliable and relatively simple as compared to traditional vibration dampers, because of the properties of the ferrofluids, you pretty much don't have any leakage. Yeah, there could be magnetic flux leakage, and depending on your applications, could be fatal. And that's it.